Let us look back to the lesson where we determined the average rate of change of Usain Bolt's 100-meter sprint, and we estimated the gradient of the displacement time graph, and we found that this gradient represented his velocity, or his speed. Now that we've got a deeper understanding of differential calculus, we will have a look at the relationship between displacement, velocity, and acceleration. If I were to watch Usain sprint and take note of his displacement every 10 meters in the race and record these coordinates on a displacement time graph, I would get the following results. If we draw a line of best fit through these points, we get the function y equals 0.33 x squared plus 7.67 x minus 1.9. Please note that this is not the optimal line of best fit, but it helps make the numbers work for the purposes of this illustration. If we differentiate this function of displacement, we get the function f prime of x being equal to 0.66x plus 7.67. To reiterate what these numbers mean, f of x is a displacement function, and f prime of x is a velocity function. We can interpret this finding by analysing the y values on the velocity function. Note that these y values correspond to the gradient of the displacement function. This is exactly what we would expect, as we already know that the gradient of a displacement function represents velocity, and that if we differentiate a function, those y values will tell us the gradient on our original function. Here, we can see the direct relationship between displacement and velocity. If we were to differentiate the velocity function, this would tell us how the velocity function is changing. And if you just think about it for a moment, the way we describe how speed changes is to use the word acceleration. If you speed up very quickly, you are accelerating fast. If you speed up slowly, you've got slow acceleration. And if you begin to slow down, we describe this as decelerating. Notice that the derivative function of velocity is f double dash or f prime prime of x being equal to 0.66. This is known as the acceleration function. In this context, you could draw the conclusion that Usain is accelerating at a rate of 0.66 meters per second, and that his initial speed was 7.67 meters per second. We can read this directly from the velocity function. And the result of the acceleration function told us how the velocity is changing. We can critically analyze this in the slope of the displacement function, where if the slope becomes steeper, we are accelerating. We can see that this slope is increasing at a steady rate of 0.66 meters per second precisely, as illustrated by the acceleration function. To simplify this concept when applying it to a problem, we can use the acronym DIVA or DVA, where the order of these letters indicates the order of the functions when we differentiate. We're just having a look at an example here where we're throwing a basketball in the air from the top of a 25-meter building. We're told that the relative position to the ground is given by this equation, where x of t, t is time in seconds, and it is a negative parabola. So 25 plus 20t minus 5t squared. First part of the question here is saying determine the average rate of change in the first second. So really what that's saying is what is the rate of change on average when we've gone from 0 to 1. And so I'm going to have to determine those x and y values and substitute them in as if I was just calculating the gradient between two x and y points. In this term, a t and x of t points. Okay, so we get a solution there for A, which we get 15. So you'd say, therefore, the average rate of change, would be 15 meters per second. Part B of the question here says, determine the velocity function, hence identify the initial speed of the basketball. And here, I'm given a displacement function, which is x of t equals 25 plus 20t minus 5t squared. And I'm just going to bring this acronym up again. DVA or DVA. I don't know, however you want to remember it. You've got displacement, you've got velocity, you've got acceleration. Okay, when you've got displacement and you want to find out velocity, you take the derivative and you get to velocity. If you want to work out the acceleration and you've got velocity, you need to differentiate again. So part B, I'm asked to determine the velocity function, hence identify the initial speed. I'm going to differentiate because I want to know what the velocity is. And I'm just going to get 20 minus 10t. And so determine the initial velocity. What I need to do is I need to let t equal 0. Okay, and we can somewhat read it from the question here. We know that it's just going to be 20 because that's what it initially is. That's that y-intercept value. But to do it rigorously, you would substitute in the point 0. And so x prime of 0 is equal to just 20 minus 10 times by 0. So you'd say it's equal to 20. Therefore, initial speed is 20 meters per second. So initially, that's how fast the basketball is moving. Thirdly, determine the acceleration function and hence state the rate of acceleration of the basketball. And so really what I'm going to do here is I'm just going to differentiate again, because if I'm at a velocity and I want to determine acceleration, I just differentiate once more, and I'm going to get negative 10. That's what I'm going to get, negative 10. And it's saying state the rate of acceleration of the basketball. Well, that is the rate. I would say, therefore, the rate of acceleration is negative 10 meters per second.